Mind, spirit, or mechanics, the quantum leap from void to being. Chapter 8. Quantum Mechanics and the Foundations of Becoming. Quantum mechanics is the most successful physical theory ever devised. Its predictions have been confirmed with extraordinary precision, sometimes to more than 10 decimal places, and it underlies nearly every modern technology: semiconductors, lasers, MRI machines, nuclear energy, GPS, and the transistors that make digital computing possible. Yet it is also the most philosophically puzzling theory in physics, because its core ideas, superposition, entanglement, wave function collapse, complementarity, uncertainty, describe a world that looks nothing like everyday experience. This chapter does not argue that the brain is a quantum computer, or that consciousness is a quantum effect, or that people can manipulate reality through quantum means. Those claims are popular in some circles, but not supported by evidence. Instead, this chapter argues that the formal structure of quantum mechanics, the mathematical pattern describing how systems move from potential to actuality, provides the clearest structural analogy for how humans move from indecision to decision, from possibility to will, from latent identity to action. Let us begin with the basics, in the plainest language possible. In classical physics, Newton's physics, the physics of planets and billiard balls, a system is always in a definite state. A ball has a definite position and a definite velocity. If you know both at one moment, you can calculate its future with perfect accuracy. The classical universe is a giant machine, deterministic, predictable, and fully described by the positions and momenta of its particles. Quantum mechanics breaks this picture. In quantum physics, a system is not usually in a definite state. Instead, it exists in a superposition, a combination of all the states it could be found in when measured. A quantum particle does not have a definite position until it is measured. Instead, it has a probability distribution over all possible positions, encoded in a mathematical object called the wave function. The wave function describes not what the particle is doing but what it might do, the full range of its potentials. When a measurement occurs, the wave function collapses. The cloud of possibilities resolves into a single outcome, and the particle appears at a specific location. This collapse is instantaneous, discontinuous, and, in the standard Copenhagen interpretation, fundamentally random. You can calculate probabilities, but not certainties. The quantum jump is the most dramatic example. When an electron moves from one energy level to another, it does not slide gradually. It jumps, instantly, without passing through intermediate states. One moment it is in one state, the next moment it is in another. The jump occurs when the system reaches a threshold, when it absorbs or emits a photon of the right energy, and the outcome is probabilistic. You can calculate the likelihood of the jump, but not the exact moment it will happen. Before the jump, the system is in a state of potential, a superposition of possible transitions. After the jump, it is in a definite new state. The transition itself is a mystery, a point where continuous mathematics meets discontinuous reality. Now consider the structural parallels to human experience. Before a real decision, the mind is in a state of potential, a metaphorical superposition of all the possible choices, actions, and futures that might unfold. The mind oscillates among these possibilities, weighing them, feeling them, imagining them, without committing. This state is uncomfortable, anxious, uncertain, suspended. Then the decision happens, and it feels like a jump, a discontinuous shift from one state to another. You are undecided, and then you are decided. The transition is often abrupt and surprising. You did not know which way you would go until you went, and it is practically irreversible. Once the decision is made, the prior state of genuine indecision is hard to recover. The analogy to quantum collapse is not literal. The brain does not operate through quantum processes at this scale, but structural. The pattern is the same. The Heisenberg uncertainty principle offers another parallel. In quantum mechanics, certain pairs of properties, like position and momentum, cannot both be known with unlimited precision. The more precisely you know one, the less precisely you can know the other. This is not a technological limitation, it is built into reality. Human experience shows a similar complementarity. The more precisely you define your intention, the more firmly you commit to a specific course, the less freedom you retain to explore alternatives. The more clearly you know what you want, the less clearly you can imagine what you might have wanted instead. Commitment narrows possibility. It transforms a field of open potential into a definite trajectory. This is not quantum physics, it is cognitive dynamics. But the structure, the trade-off between definiteness and openness, is the same. The concept of decoherence adds another layer. In quantum mechanics, decoherence occurs when a quantum system interacts with its environment in a way that destroys superposition and forces classical behavior. Decoherence does not require a conscious observer. It happens naturally whenever a system becomes entangled with its surroundings. It explains why macroscopic objects behave classically even though they are made of quantum particles. In human life, a similar process occurs when an internal decision becomes entangled with the external world. When you speak your intention aloud, take the first step, sign the contract, or cross the threshold, the decision becomes embedded in social, physical, and psychological consequences. Before this entanglement, the decision is still reversible. You can still change your mind. Afterward, the decision becomes effectively irreversible, stabilized by its interactions with the world. This is how potential becomes actual, how an inner leap becomes an outer reality. It is essential to be clear about what this analogy does not claim. It does not claim that the brain is a quantum computer. While some theorists, notably Roger Penrose and Stuart Hameroff, have proposed quantum processes in neuronal microtubules as the basis of consciousness, this idea remains speculative and unsupported by current evidence. The brain operates at temperatures, scales, and timescales where quantum coherence is extremely difficult to maintain. Most neuroscientists and physicists consider quantum models of consciousness premature. The argument here is not that the brain uses quantum mechanics, but that the brain recapitulates the same formal pattern that quantum mechanics describes: the transition from potential to actuality, from superposition to collapse, from openness to commitment. This pattern is universal. It appears wherever complex systems navigate fields of possibility and resolve into definite states. It is the pattern of becoming, the pattern of the quantum leap, and it operates at every scale, from the electron to the human mind.